Hello, everyone. In this video, we're going to look at that second part on our first page of section 5.6 on numerical integration. So now we're going to look at what's called the midpoint rule. So again, we're going to let delta x represent the change of x between 2 points in our subdivision, and n be the number of subdivisions. So again, similar to the previous problem that we looked at, we know that delta x is going to be equal to the distance. Again, we're starting with a to b. So from b to a, b minus a over n. All right, so midpoint rule. So in the midpoint rule, we're going to approximate that integral or the area under the curve from a to b using rectangles where the height is computed at the midpoint of the interval that we are subdividing. So let's go ahead and draw in those rectangles. So what do those rectangles look like? Well, they're actually dashed out here, but go ahead and draw over them for yourself on your paper so that you can see here. So notice what's happening. The height of each rectangle is being computed at the middle point of each interval in our subdivision, right? So we can draw those out. Okay, cool. So just some different notation. We're letting m sub n be the value of that integral using the midpoint rule with n rectangles. So I'm just going to write that out. So midpoint, we call it midpoint rule. We could even go further to say midpoint rule approximation with n rectangles. So that n tells us how many rectangles we're using. So that's equivalent, that's equal to the integral, in this case, from a to b. No, maybe not equal. It's an approximation of the integral from a to b of f of x dx using those midpoint rectangles. Okay, so what does that formula actually look like? Well, let's set it up here first. So just like we did using the trapezoid rule, let's go ahead and write out the area for just some example of some of these midpoint rectangles. So in order to compute the area of these rectangles, we need the width and the height. So the width we already know. So the width is going to be this delta x. That's just the notation that we're given, and we even have a nice formula for it there. But then we need the height. So in order to find the height of the rectangle, well, we need to talk or have a way to talk about the middle point of this interval from x0 to x1. So I'm going to call that middle point x sub 1 bar. So in the second rectangle, I'm going to call that point x sub 2 bar, x sub 3 bar, all the way to x sub n bar. So I'm labeling with that index on that right side. Okay, so now what is x sub I bar? So let's write that out. So the height, we need to use x sub I bar. So that would be the midpoint. In words, the midpoint of ith interval. Okay, so how would we compute that? Well, in order to compute that midpoint, what we do is we use the two endpoints of the interval. So if our generic rectangle here, so we have x sub I minus 1, x sub I. So the midpoint, we're calling x bar sub I. So x bar sub I want a little formula for it. To compute that midpoint, what we do is a similar method of computing that length of an interval. But now rather than subtract that difference, we add it together. So we should think of computing x sub I bar as computing the average between x sub I minus 1 and x sub I. Because the average of these two numbers is going to be that number in between. So compute an average. You might have seen this before. You add up your numbers. So x sub I minus 1 plus x sub I divided by 2. So this is going to be that midpoint. Okay, so how are we going to use that here? Well, that's going to be used to determine the height of our rectangle. So let's go ahead and write out the sum of those rectangles. So I'll call it, say, we'll call this R1, R2, and I'll use this kind of sloppy notation where I'm going to write R1 as the rectangle, but also the area of the rectangle. So what does R1 look like? Well, we need the width, which is delta x, and then the height. So we're going to evaluate the function at x sub 1 bar. So that's going to be R1. R2, what does that look like? Well, delta x, the width, times f of x sub 2 bar. So we're just going to continue until we have all of our n rectangles. That would look like delta x, f of x sub n bar. Okay, so now, similar to the trapezoid rule, we see that there is a delta x term in each of the terms in our sum. So I can factor that out. So I just get delta x times f of x sub 1 bar plus f of x sub 2 bar plus all the way until we reach f of x sub n bar. All right. So there we have just created or derived the formula for the midpoint rule. All right, so in the upcoming videos, we're going to look at some examples for using these formulas and numerical integration methods for approximating areas under curves. Thanks for watching.